Good morning, Sir Alvin Mahawan, and good morning, classmates. Today I will discuss about the life chemical evolution and climate change. So, as far as we know, Earth seems to be the only planet in the solar system with life. The origin and development of life are an important part of our planet's story. Life arose early in Earth history, and living organisms have been interacting with their environment for billions of years. We recognize that life forms have evolved to adapt to the environment of Earth, and we are now beginning to realize that Earth itself has been changed in important ways by the presence of living matter. The study of the co-evolution of life on our planet is one of the subjects of the modern science of astrobiology. The origin of life. The record of the birth of life on Earth has been lost in the restless motions of the crust. According to chemical evidence, by the time the oldest surviving rocks were formed around 3.9 billion years ago, life already existed. At 3.5 billion years ago, life had achieved the sophistication to build large colonies called stromatolites, a form so successful that stromatolites still grow on Earth today. But few rocks survive from these ancient times, and abundant fossils have been preserved only during the past 600 million years, less than 15% of our planet's history. There is a little direct evidence about the actual origin of life. We know that the atmosphere of early Earth, unlike today's, contained abundant carbon dioxide and some methane, but no oxygen gas. In the absence of oxygen, many complex chemical reactions are possible that lead to the production of amino acids, proteins, and other chemical building blocks of life. Therefore, it seems likely that these chemical building blocks were available very early in Earth's history, and they would have combined to make living organisms. For tens of millions of years after Earth's formation, life, perhaps little more than large molecules like the viruses of today, probably existed in warm, nutrient-rich seas living off accumulated organic chemicals. When this easily accessible food became depleted, life began the long evolutionary road that led to the vast numbers of different organisms on Earth today. As it did so, life began influence the chemical composition of the atmosphere. In addition to the study of life history as revealed by chemical and fossil evidence in ancient rocks, scientists use tools from the rapidly advancing field of genetic and genomics, the study of the genetic code that is shared by all life on Earth. While each individual has a unique set of genes, which is why genetic fingerprinting is so useful from the crime, we also have genetic traits in common. Your genome, the complete map of the DNA in your body, is identical at the 99.9 level. At the 99 level, human and chimpanzee genomes are the same. By looking at the gene sequences of many organisms, we can determine that all life on Earth is descendant from a common ancestor. And we can use the genetic variation among species as a measure of how closely different species are related. These genetic analysis tools have allowed the scientists construct what is called the tree of life. This diagram illustrates the way the organisms are related by examining one sequence of the nucleic acid RNA that all species have in common. This figure shows that life on Earth is dominated by microscopic creatures that you have probably never heard of. Note that the plant and animal kingdoms are just two little branches of the far right. Most of the diversity of life and most of our evolution has taken place at the microbial level. Indeed, it may surprise you to know that there are more microbes in a bucket of soil than there are stars in the galaxy. The aliens that are most likely to be out there are microbes. Such genetic studies lead to other interesting conclusions as well. For example, it appears that the earliest surviving terrestrial life forms were all adapted to live at high temperatures. Some biologists think that life might actually have begun in locations on our planet that were extremely hot. Yet another intriguing possibility is that life began on Mars rather than Earth and was seeded onto our planet by meteorites traveling from Mars to Earth. Mars rocks are still making their way to Earth, but so far none has shown evidence of serving as a spaceship to carry microorganisms from Mars to Earth. The evolution of the atmosphere. One of the key steps in the evolution of life on Earth was development of blue-green algae, a very successful life form that takes in carbon dioxide from the environment and releases oxygen as a waste product. Since successful microorganisms have proliferated, giving rise to all the life forms we call plants. Since the energy for making new plant material from chemical building blocks come from the sunlight, we call the process photosynthesis. Studies of the chemistry of ancient rocks show that Earth's atmosphere lacked abundant free oxygen until about 2 billion years ago, despite the presence of plants releasing oxygen by photosynthesis. Apparently, chemical reaction with Earth's crust removed the oxygen gas as quickly as it formed. Slowly, however, the increasing evolutionary sophistication of life led to a growth in the plant population, and thus increased oxygen production. At the same time, it appears that increased geological activity led to heavy erosion of our planet's surface. This buried much of the plant carbon before it could recombine with oxygen to form carbon dioxide. Free oxygen began accumulating in the atmosphere about 2 billion years ago, and the increased amount of this gas led to the formation of Earth's ozone layer. Recall that ozone is a triple molecule of oxygen, which protects the surface from deadly solar ultraviolet light. Before that, it was unthinkable for life to venture outside the protective oceans, so the land masses of Earth were barren. The presence of oxygen enhanced ozone, thus allowed colonization of the land. It also made possible a tremendous proliferation of animals, which live by taking in and using the organic materials produced by plants as their own energy source. As animals evolved in an environment increasingly rich in oxygen, they were able to develop techniques for breathing oxygen directly from the atmosphere. Greenhouse effect and global warming. We have the special interest in the dioxide content of the atmosphere because of the key role this gas plays in retaining heat from the sun through a process called greenhouse effect. To understand how the greenhouse effect works, consider the fate of sunlight that strikes the surface of Earth. The light penetrates our atmosphere, is absorbed by the ground, and hits the surface layers. At the temperature of Earth's surface, that energy is then re-emitted as infrared of heat radiation. However, the molecules of our atmosphere which allow visible light through are good at absorbing infrared energy. As a result, carbon dioxide along with the methane and water vapor acts like a blanket, trapping heat in the atmosphere and impeding its flows back to space. To maintain an energy balance, the temperature of the surface and lower atmosphere must increase until the total energy radiated by Earth to space equals the energy received from the Sun. The more carbon dioxide there is in our atmosphere, the higher the temperature at which Earth's surface reaches a new balance. The greenhouse effect in a planetary atmosphere is similar to the heating of gardener's greenhouse or the inside of a car left out in the sun with the windows rolled up. In these examples, the window glass plays the role of greenhouse gases, letting sunlight and in but reducing the outward flow of heat radiation. As a result, a greenhouse or car interior winds up much hotter than would be expected from the heating of sunlight alone. On Earth, the current greenhouse effect elevates the surface temperature by about 23 degrees Celsius. Without this, the greenhouse effect, the average surface temperature will be well below freezing, and Earth will be locked in a global ice age. So that's the good news. The bad news is that the heating due to the greenhouse effect is increasing. Modern industrial society depends on energy extracted from burning fossil fuels. In effect, we are exploiting the energy-rich material created by photosynthesis tens of millions of years ago. As these ancient coal and oil deposits are oxidized, burned using oxygen, large quantities of carbon dioxide are released into the atmosphere. The problem is exacerbated by widespread destruction of tropical forests, which we depend on to the extra carbon dioxide from the atmosphere and replenish our supply of oxygen. In the past century of increased industrial and agricultural development, the amount of carbon dioxide in the atmosphere increased by about 30% and continues to rise at more than 0.5% per year. Before the end of present century, Earth's carbon dioxide level is predicted to reach twice the value it had before the Industrial Revolution. The consequences of such an increase for Earth's surface and atmosphere and the creatures who live there are likely to be complex changes in climate and may be catastrophic for many species. Many groups of scientists are now studying the effects of such global warming with elaborate computer models, and climate change has emerged as the greatest known threat, barring nuclear war, to both industrial civilization and the ecology of our planet. Already, climate change is widely apparent. Around the world, temperature records are constantly set and broken. All but one, the, all but one of the hottest recorded years have taken place since 2000. Glaciers are retreating, and the Arctic Sea ice is now much thinner than when it was first explored with nuclear submarines in 1950s. Rising sea levels from both melting glacier and expansion of the water as its temperature rises pose one of the most immediate threats, and many coastal cities have plans to build dikes or seawalls to hold back and expecting flooding. The rate of temperature increase is without historical precedent, and we are rapidly entering unknown territory where human activities are leading to the highest temperature on Earth in more than 50 million years. Human impacts on our planet. Earth is so large and has been here for so long that some people have trouble accepting that humans are really changing the planet, its atmosphere, and its climate. They are surprised to learn, for example, that the carbon dioxide released from burning fossil fuels is 100 times greater than the emitted by volcanoes. But the data clearly tell the story that our climate is changing rapidly and that almost all of the change is a result of human activity. This is not the first time that humans have altered our environment dramatically. Some of the greatest changes were caused by our ancestors before the development of modern industrial society. If aliens had visited Earth 50,000 years ago, they would have seen much of the planet supporting large animals of the sort that now only survive in Africa. The plains of Australia were occupied by giant marsupials such as Diprotodon and Zygomatorus. the size of our elephants today, and a species of kangaroo that stood 10 feet high. North America and North Asia hosted mammoths, saber-toothed cats, mastodons, and giant sloths, and even camels. The islands of Pacific teemed with large birds, and vast forests cover what are now the form of Europe and China. Early human hunters killed many large mammals and marsupials. Early farmers cut down I, our early farmers cut down most of the forest, and the Polynesians' expansion across the Pacific domed the population of large birds. An even greater mass extension is underway as a result of rapid climate change. In recognition of our impact on the environment, scientists have proposed giving a new name to the current epoch, the Anthropocene, when human activity is started to have a significant global impact. Although not an officially approved name, the concept of Anthropocene is useful for recognizing what that we humans now represent the dominant influence on our planet atmospheres and ecology, for better or for worse. Cosmic influences on the of Earth. In discussing Earth geology, earlier in this chapter, we dealt only with the effects of internal forces expressed through the processes of plate tectonics and volcanism. On the Moon, in contrast, we see primarily craters produced by the impacts of interplanetary debris such as asteroids and comets. Why don't we see more evidence on Earth of the kinds of impact craters that are so prominent on the Moon and other worlds? So, we are the craters on Earth. It is not possible that Earth escaped being struck by the interplanetary debris that has pockmarked the Moon. From a cosmic perspective, the Moon is almost next door. Our atmosphere does make small pieces of cosmic debris burned up, which we see as meteors, commonly called shooting stars. But the layers of our air provide no shield against the large impacts that form craters several kilometers in diameter and are common on the Moon. In the course of its history, Earth must therefore have been impacted as heavily as the Moon. The difference is that on Earth, these craters are destroyed by our active geology before they can accumulate. As plate tectonics constantly renews our crust, evidence of past cratering events is slowly erased. Only in the past few decades, some geologists succeeded in identifying the eroded remnants of many impact craters. Even more recent in our realization that, over the history of Earth, these impacts have had an important influence on the evolution of life. Recent impacts. The collision of interplanetary debris with Earth is not a hypothetical idea. Evidence of relatively recent impacts can be found in our planet's surface. One well-studied historic collision took place on June 30, 1908, near the Tunguska River in Siberia. In this desolate region, there was a remarkable explosion in the atmosphere about 8 kilometers above the surface. The shock wave flattened more than 1,000 square kilometers of forest. Herds of reindeer and other animals were killed, and a man at a trading post 80 kilometers from the blast was thrown from his chair and knocked unconscious. The blast wave spread around the world as recorded by instruments designed to measure changes in atmospheric pressure. Despite this violence, no crater were formed by the Tunguska explosion. Shattered by atmospheric pressure, the stony projectile with a mass of approximately 10,000 tons disintegrated above our planet's surface to create a blast equivalent to a P5 megaton nuclear bomb. Had it been smaller or more fragile, the impacting body would have dissipated its energy at high altitude and probably attracted no attention. Today, such high-altitude atmospheric explosions are monitored regularly by military surveillance systems. It had been larger or made stronger materials such as a metal. The Tunguska projectile would have penetrated all the way to the surface of Earth and exploded to form a crater. Instead, only the heat and shock of the atmospheric explosion reached the surface. But the devastation it left behind in Siberia bore witness to the power of such impacts. Imagine if the same rocky impactor had exploded over New York City in 1980. History books might today record it as one of the most deadly events in human history. Tens of thousands of people witnessed directly the explosion of a smaller or 20-meter projectile over the Russian city of Chelyabinsk on an early winter morning in 2013. It exploded at a height of 21 kilometers in a burst of light brighter than the sun, and the shock wave of the zero point 0.5 megaton explosion broke tens of thousands of windows and sent hundreds of people to the hospital. Rock fragments, meteorites, were easily collected by people in the area after the blast because they landed on fresh snow. The best known recent crater on Earth was formed about 50,000 years ago in Arizona. The projectile in this case was a lump of iron about 40 kilometers in diameter, now called Meteor Crater and a major tourist attraction on the way to the Grand Canyon. The crater is about a mile across and has all the features associated with similar sized lunar impacts. Crater Meteor crater is one of the few impact features on Earth that remains relatively intact. Some older craters are so eroded that only a trained eye can distinguish them. Nevertheless, more than 150 have been identified. Mass extinction. The impact that produced Meteor Crater would have been dramatic indeed to any humans who witnessed it from a safe distance, since the energy release was equivalent to a 10 megaton nuclear bomb. But such explosions are devastating only in their local areas. They have no global consequences. Much larger and rarer impacts, however, can disturb the ecological balance of the entire planet and thus influence the course of evolution. The best documented large impact took place 65 million years ago, at the end of what is now called the Cretaceous period of geological history. This time in the history of life on Earth was marked by a mass extinction in which more than half of the species on our planet died out. There are a dozen or more mass extinction in geological record, but this particular event, nicknamed the Great Dying, has always intrigued paleontologists because it marks the end of the dinosaur age. For tens of millions of years, this great creature had flourished and dominated. Then they suddenly disappeared, along with many other species, and thereafter mammals began the development and diversification that ultimately lead to all of us. The object that collided with Earth at the end of the Cretaceous period struck a shallow sea in what is now the Yucatan Peninsula of Mexico. Its mass must have been more than a trillion tons, determined from study of a worldwide layer of sediment deposited from the dust cloud that enveloped the planet after its impact. First identified in 1979, this sediment layer is rich in the rare metal iridium and other elements that are relatively abundant in asteroids and comets, but exceedingly rare in Earth's crust, even though it was diluted by the material that the explosion excavated from the surface of Earth. This cosmic component can be still identified. In addition, this layer of sediment contains many minerals characteristic of the temperatures and pressures of a gigantic explosion. The impact that led to extinction of dinosaurs released energy equivalent to 5 billion Hiroshima-sized nuclear bombs and excavated a crater 200 kilometers across and deep enough to penetrate through Earth's crust. This larger crater, named Chicxulub, for a small town near its center, has subsequently been buried in sediment, but its outlines can still be identified. The explosion that created the Chicxulub crater lifted about 100 trillion tons of dust in the atmosphere. We can determine this amount by measuring the thickness of the sediment layer that formed when this dust settled to the surface. Such a quantity of airborne material would have blocked sunlight completely, plunging Earth into a period of cold and darkness that lasted several months. Many plants dependent on sunlight would have died, leaving plant-eating animals without a food supply. Other worldwide effects included large-scale fires started by the hot, flying debris from the explosion that destroyed much of the planet's forests and grassland in a long period in which rainwater around the globe was acidic. It was these environmental effects rather than the explosion itself that were responsible for the mass extinction, including the demise of the dinosaurs. Impacts and the evolution of life. It is becoming clear that many, perhaps most mass extinction in Earth's long history resulted from a variety of other causes. But in the case of dinosaur killer, the cosmic impact certainly played a critical role and may have been the final straw in a series of climatic disturbances that resulted in the Great Dying. A catastrophe for one group of living things, however, may create opportunities for another group. Following each mass extinction, there is a sudden evolutionary burst and new species develop to fill the ecological niches opened by the event. 65 million years ago, our ancestors, the mammals, began to thrive when so many other species died out. We are the lucky beneficiaries of this process. Impacts by comets and asteroids represent the only mechanism we know that could cause truly global catastrophes and seriously influence the evolution of life all over the planet. As, as paleontologist Stephen Jay Gould of Harvard noted, such a perspective changes fundamentally our view of biological evolution. The central issues for the survival of a species must now include more than just in success in competing with other species and adapting to slowly changing environments, as envisioned by Darwin's ideas of natural selection. Also required is an ability to survive random global catastrophes due to impacts. is still early in its history, Earth was subject to even larger impacts from the leftover debris of planet formation. We know that the moon was struck repeatedly by objects larger than 100 kilometers in a diameter, 1,000 times more massive than the object that wiped out most terrestrial life 65 million years ago. Earth must have experienced similar large impacts during its first 700 million years of existence. Some of them were probably violent enough to strike the planet of most its atmosphere, and to boil away its ocean. Such events would sterilize the planet, destroying any life that had begun. Life may have formed and been wiped out several times before of our microbial ancestors took hold sometime about 4 billion years ago. The fact that the oldest surviving microbes on Earth are thermophiles, adapted to very high temperatures, can also be explained by such large impacts. An impact that was just a bit too small to sterilize the planet would still have destroyed anything that lived in what we consider normal environments, and only the creatures adapted to high temperatures will survive. Thus, the oldest surviving terrestrial life forms are probably the remnants of a sort of evolutionary bottleneck caused by repeated large impact early in the planet's history. Impacts in our future. The impacts by asteroids and comets that have had such a major influence on life are not necessarily a thing of the past. In the full scope of planetary history, 65 million years ago was just yesterday. Earth actually orbits the Sun within a sort of cosmic shooting gallery, and although major impacts are rare, they are by no means over. Humanity could suffer the same fate as the dinosaur, or lose a city to the much more frequent impacts like the one over Tunguska, unless we figure out a way to predict the next big impact and to protect our planet. The fact that our solar system is home to some very large planets in outer orbits may be beneficial to us. The gravitational fields of those planets can be very effective at pulling in cosmic debris and shielding us from large or more frequent impacts. Beginning in the 1990s, a few astronomers began to analyze the cosmic impact hazard and to persuade the government to support a search for potentially hazardous asteroids. Several small but sophisticated wide-field telescopes are now used for this search, which is called the NASA Space Guard Survey. Already we know that there are currently no asteroids on a collision course with Earth that are as big 10 to 15 kilometers as the one that killed the dinosaur. The Space Guard Survey now concentrates on finding smaller potential impactors. By 2015, the search had netted more than 15,000 near-Earth asteroids, including most of those larger than 1 kilometer. None of those discovered so far possess any danger to us. Of course, we cannot make a similar statement about the asteroids that have not yet been discovered, but these will be found and evaluated by one for their potential hazard. These asteroid surveys are one of the few really life and death projects carried out by astronomers with a potential to help to save our planet from future major impact. Thank you.